That's the explanation. All right, so the wavelength is going to get shorter as the wave crosses the boundary because obviously the wave is slowing down. So what happens to the wavelength within the glass as the index of refraction increases, which means as the wave slows down, that's the meaning of increase of the index of refraction. So what that means is the wavelength is going to become shorter, so the best answer becomes A. So now you got the incident ray, you got the reflected ray, and you got the refracted ray. Index of refraction for water is going to be higher, so which means that it's going to slow down in water. As the ray is coming from a less dense into more dense medium, it's going to get refracted towards the normal. As the ray is coming from more dense into less dense medium, it's going to get refracted away from the normal. All right, so the question is, how do we come up with the formula that's now came up with? So you got the incident ray coming in, and there's going to be a refraction. Take a look at the size of the wavelength. So the wavelength is going to become shorter. You got the angle of incidence. You got the angle of refraction down below. All right, so I'm just going to take this, and then we will just represent the geometry as such. So here's a wavefront for the approaching wave, and here's the wavefront in the optically denser medium. You got the angle of incidence. That could be also expressed in terms of angle of incidence can be placed over here, and you got the angle of refraction. Angle of refraction is going to go there. Notice that we'll come up with two triangles. This is one other triangle. You got the wavelength here, the original wavelength. This is the shorter wavelength. This is hypotenuse, so is this one. And no, this is the base of this one. This is the base of this one, and this will be the hypotenuse. So H is going to denote hypotenuse in that one. So I'll base the derivation based upon that little schematic that we saw. All right, so I'm just drawing my wavefronts right now. All right, so this is the wavefront for the incoming wave. This is the wavefront for the wave inside an optically dense medium. So N is going to represent our normal. All right, so this is the original wavelength. This is the shortened wavelength in an optically dense medium. All right, so this is the incident ray. And notice that the incident ray is going to be perpendicular to the wavefront over here. All right, so these two angles are the same. This is the refracted ray. This is going to be perpendicular to that wavefront over there. All right, so this angle is the same as that angle. All right, so depending upon how you're looking at it, this could be the height of our triangle. This would be the base. This is going to be the hypotenuse. This is our second triangle. So this is the height. This is the base. This is once again the hypotenuse. So H is going to represent the hypotenuse. Both these triangles will have the same hypotenuse. So H is our hypotenuse. All right, so we know that the first wavelength is going to be larger than the second wavelength. Now we will have to come up with expressions for sine of the angle of the first one. So the sine of the angle of the first one, sine of this is going to be the opposite over the hypotenuse. So it's going to be lambda 1, the first wavelength divided by the hypotenuse. That's it. And the sine of the second angle is going to be, once again, this is the opposite, which is the second wavelength over the hypotenuse. All right, so what do we have in common between these two? So H is going to be in common between those two. H is going to be in common between those two. All right, so we got a spotlight. So these are going to be in common. All right, so those will be in common between those two. So equating everything to H. All right, so now we got to make an adjustment, express the wavelengths in terms of the wave speeds. And knowing that we got the frequency on both sides, frequencies will cancel. And then we can express the speeds in terms of indices of refraction by dividing both sides by C. So C over V is going to be N, so just invert both sides. Now we got our expression for the inverted Snell's law. So which means that you can invert both sides. In doing so, you end up getting the Snell's law. All right, let's do a simple problem. This is going to be problem number 1 that we're looking at. So what do we have? We got a light ray striking the boundary of the water surface in an angle of 46 degrees. So we got our 46 degrees with respect to normal. Find the angle of refraction. So the angle of refraction in this case is going to be theta 2. And 1 is 1 for air, and 2 is 1.33 for water. All right, so we start off with the Snell's law. Solve for the second angle. Get rid of N2 from both sides. And now isolate theta 2 by taking the inverse of sine, and that's it. That's it. Mathematically, this is as far as you go, and then plug the numbers in. All right, so in this case, we reverse the direction now. It's going to be coming from water into air. So if that's the case, the question is, what is the index of refraction? It's the same exact formula. Formulation is exactly the same, except just plug the numbers into that. Total internal reflection. Well, whether the light is going to be totally internally reflected or refracted depends on the critical angle. So let's talk about the critical angle. What is the critical angle? Critical angle is critical to whether the light gets internally reflected or captured by the material itself, or it gets refracted out, which means that it escapes from the material itself. At the critical angle, refracted light is going to be 90 degrees to the normal, or it's going to be parallel to the surface of the boundary that you're looking at. Once again, if the angle of incidence is smaller than the critical angle, light refracts, which means that it escapes. If the angle of incidence is larger than the critical angle, light simply is going to be totally internally reflected, which means that the light will be captured by the material itself. There's a different way of looking at it. M1, one of them is M1, the other one is N2. N2 has to be a larger index of refraction than M1 for this to work. So the light source is going to be within that material, and this is your critical angle. An angle smaller than the critical angle, light refracts, and an angle larger than the critical angle, the light simply becomes internally reflected, which means that it becomes captured by the material itself. So let's come up with a mathematical expression for it, internal reflection. All right, so here's the incident ray. Reflected ray is going to be 90 degrees to the normal, so it's parallel to the surface of the boundary. So that's going to be our critical angle. And the angle of refraction is 90 degrees. By using the Snell's law, we can come up with an expression for the critical angle. Angle of incidence is going to be theta 1. Angle of incidence is the critical angle. Theta 2 is going to be the angle of refraction, which is right here, so it's going to be 90 degrees. Sine of 90 degrees is 1. All right, so M1 is going to be larger than N2. So we came up with an expression for the critical angle. So solve for the critical angle, and we're done. All right, N2 in this case, if it's air, it's going to be 1. So we can further simplify the equation to this. All right, so this is our critical angle. One of the things that we need to notice is the larger the index of refraction is, the smaller the critical angle becomes. All right, so slower the light moves inside a material, the smaller the critical angle is. That's what it means. So that becomes our conclusion. So the bigger the index of refraction is, the smaller the critical angle becomes. So index of refraction for diamond is almost 2.5. Air is almost, obviously 1, almost 1. So which means that the critical angle for diamond is going to be significantly smaller than air. So at angles larger than the critical angle, we will end up getting total internal reflection. So in this case, the angle of incidence will be the same as the angle of reflection. So angles larger than the critical angle, like is internal reflected. We got a case study. We're going to do total internal reflection. Notice that this is cut at, this is a prism, cut at 45 degree angles. There's an incoming ray, and it's hitting the surface at 95. It's a 45 degree angle, and then it's just beautifully, it gets refracted. It comes in and then gets refracted out at that angle. Also, you can, it's coming at an angle, 45 degree angle with respect to the surface. You end up getting a nice little reflection, and then one more time it gets reflected and then gets refracted out. So speaking of a prism, let's figure out its critical angle. All right, remember, if the light is coming in at an angle larger than the critical angle, it's going to get refracted. At an angle smaller than the critical angle, it's going to get internally reflected. So this one is coming in, it gets internally reflected, and then it gets refracted out. So this is a 90 degree angle, this is 45 degrees. So at angles smaller, larger than the critical angle, it's going to get refracted. It's going to get internally reflected. All right, so light is inside, a beam of light is propagating through a glass prism, so index of refraction is going to be 1.5, so this is what we got. And N2 is the outside, it's going to be air, so we got glass and air. So what is the critical angle for this one? All right, so critical angle for this one is the one that we're interested in. So I'm using this as an excuse to give you the same derivation as I gave you before. So M1 in this case is going to be larger than N2. All right, so theta 1 is going to give us the critical angle. That's what we're interested in. Theta 2 is going to be 90 degrees. Hit the critical angle. And then this is the same exact formula that we came up with. So plug the numbers in. And then when you plug the numbers in, we'll get a critical angle, which is going to be something. Oh, I was hoping that I did the work there. I just wanted to see what the actual number was. Because obviously, for the work for this to happen, we got 45 degrees. Critical angle has to be smaller than 45 degrees for us to be able to get this kind of internal reflection right there. So I just do the work, just figure it out, check to see what the number is. Binoculars obviously use these lenses, prisms usually. All right, and you're able to, they almost work like a mirror in that sense. All right, so the light is going to get reflected around. It's reflected and refracted, reflected and refracted. It's kind of neat.
Which one of these do you think will be set in platinum? Classic mounting, round, classic mounting, set in platinum.
All right, so the diamond sparkle.
It's really pretty.
I hereby pronounce you engaged.
This is the one. Looking at ring.
And notice that sparkle is something that you see only at a certain angle. Diamonds are cut, which means the sparkle is light is generated by the light escaping from the material. So,
Looking at ring.
and the light is going to escape from only certain angles. Part of the reason is because of the way the diamonds are cut. At those angles, you will get to see the sparkle. So you will get to see the sparkle every time you move the diamond around back and forth. And the main reason why the diamonds sparkle is because they are also really good at capturing light. They have an extremely large index of refraction, which means that their critical angles are going to be extremely, extremely small. And they're cut in such a way that much of the light entering into the medium is going to get internally reflected inside diamond all over the place. So they are very good at capturing light, as the light is just bouncing all over the place inside diamond only at certain angles, smaller than the critical angle. The light is going to escape from the material itself, so they will get refracted at angles smaller than the critical angle. At angles larger than the critical angle, they will just bounce around. And so that's the reason why. All right, I'm hoping that I actually did this mathematically. I'm not sure. All right, so what do we have? We got the light propagating inside diamond, strikes the boundary, the diamond to air interface, and an angle 28 degrees. So will part of the beam enter the air, which means that will it get refracted, or will it be totally internally reflected? And then what would happen if you were to place it into water? All right, so index of refraction for diamond, 2.42. Air is 1. All right, so angle of incidence is 28 degrees. So let's use the original formula for the critical angle. So plug in the numbers. When you plug the numbers in, we end up getting an expression for the critical angle. It's like 24, 25 degrees, more or less. All right, so critical angle is 24, 25 degrees. The angle of incidence is going to be 28 degrees, so which means that the light is going to be internally reflected. That's the case. So which means that this thing is going to capture light. So what if now we place diamond into water? What's going to happen? All right, so what happens to the critical angle if that's the case? So once again, we plug the numbers in, and now our critical angle is going to be 33, 34. It's about 33 degrees. Angle of incidence is 28 degrees. Angle of critical angle is going to be 33 degrees, which means that the light is going to escape from the material. It's going to be refracted, so it's not going to sparkle as much. That's what it means. So diamond in water is not going to sparkle as much. All right, so fiber optics, once again, they have an extremely high index of refraction. Because the index of refraction is extremely high, the critical angle is going to be very small. And the light comes in at an angle in such a way that much of the light is going to be internally reflected. So we end up getting an internal reflection. All right, let's play this game about safety in oceans or the seas or whatever. Let's look at things from the perspective of a shark. All right, speaking of looking at things from the perspective of a shark, imagine that there's a shark here. Not only from the shark is going to be able to see what's under the surface, so they can see the reflection, total internal reflection is taking place. So if there's something hidden here, by looking at the surface, they can actually see it. They're hunting something that they're interested in. So at angles larger than the critical angle, they can actually explore what's going on within the ocean itself. Right at the critical angle, they could see what's happening right at the surface. They could see if there's someone who's actually swimming or on a boat. And they could also see things all the way up to the shoreline. This is kind of interesting. And also they could see what's going on above the surface. So they certainly have a certain greater advantage in terms of being hunted.